talk is by Burlingame and Fitzsimmons on risk variant policy switching to exceed reward thresholds.
So I'm Breland, and I'm going to be discussing work that I've done with my advisor, Reed Simmons, at Carnegie Mellon Robotics Institute. And to sort of put these words into a more concrete example, when you think about an agent having to exceed a reward, you could think about maybe a pizza delivery domain, and now you have to get to this delivery location within a certain amount of time. So you want to do that within that amount of time, otherwise, it's going to be detrimental to your business. So this is kind of a threshold that's important for the agent personally. So the kind of different domains that we care about when exceeding thresholds or you can kind of think of these competitive domains. So these are domains where the difference between second and last might be actually negligible. So you want to do all you can to win. So a nice example of this is you're not doing sort of the best on average, like in an arcade game, but you're actually trying to achieve this top score. So it's natural for an agent to want to take risk to be able to accomplish this goal. You can kind of think of things in terms of soccer, where now you maybe are playing more offensively when you're down, or you're switching to this more defensive strategy when you're ahead. So in hockey, a lot of times there's this sort of undetermined amount of time of when it's best to pull your goalkeeper to gain an offensive player in hopes of scoring a tying goal to win. And as we kind of saw yesterday, that this happens in soccer as well, where the goalie actually became an offensive player. So this is a very sort of risky thing to do. It's not always clear when the best time it would be to do this, so we're kind of answering this question in a more principled way. So if we go back to our pizza delivery domain, you could see that the idea of taking risk here is you're maybe going the average speed and you're running into some unexpected traffic. So a risky action might be to speed. And by doing this, you might suffer getting pulled over by a police officer, and then you're going to get there in an even slower time than if you hadn't have sped at all to begin with. So now, if you're doing sort of the expectation of this value over time, you might be going this speed limit at every single time step in the environment. This would be an example of a risk-neutral behavior. And if you're deciding to take risk, maybe you're taking a risky action every single time in your state. And you can get very lucky. You could just speed all the way and get there in a very short amount of time, or you could be very unlucky and a cop is pulling you over at every intersection, and now it would have probably been best to not choose to begin. So there's a lot higher variance when you take risk. You have this chance of this higher upside, but at the same time, this downside could be pretty detrimental. So the applications that I'll be focusing on in this talk are these thresholded reward domains. And specifically, I'm going to be focusing on a suite of policies that are of these varying levels of risk. And I'll tell you a little later how I'm able to generate these policies. But the main sort of point of the method that I'm showing is this ability to switch between these policies at runtime to be able to accomplish the goal of maximizing this expected reward threshold. So given a current state, which is kind of your progress towards the goal, and then given your current running cumulative reward, which is how far you are away from the threshold, when would you make this decision to switch between these policies of varying risks to exceed the threshold? So we're making an assumption that the world is going to be modeled as a Markov decision process. So to be consistent with the pizza domain, we can define our states as a grid world. We'll define various actions, and we define these transition probabilities where there is a small probability of actually getting stuck, and then other probabilities of exceeding and going on in the environment. So the difference between the risky action and the less risky action in this case was that example of speeding. So you have this small probability of making it further, but you're doing so at sort of this higher probability of actually getting stuck in the environment. In this case, if you think of reward as a cost, maybe for, yep.
Are you considering deterministic action selections or mixed strategies or stochastic action selections in your policy?
So in the policy, these are, I guess, they become deterministic, and so it's just a matter of switching and grabbing that one action once they've been solved for.
Right, but for example, you can't flip a coin and half of the time you speed and half of the time you don't speed. You don't consider that.
Well, we consider that from the switching. So it kind of ends up emulating that behavior by doing the switching actions. So a sort of straightforward approach to solving this problem is just adding this cumulative reward or time to the state space, which has been looked at in more detail by Colin McMillan in his work with these thresholded rewarded MDPs. But the problem that could happen here is if you have a more realistic domain, the state space grows quite large and can be intractable for these more realistic domains. So our approach is one where we're looking at it in a different way, which is instead of having this static policy where we're following it every time, maybe when the agent is doing particularly well, you want to be more conservative, and when the agent is doing particularly unlucky, you might want to take more risk. So we have this idea of switching between multiple policies to create this kind of dynamic action at runtime. So the main trade-off in this work is we're trading off some computation and somewhat less optimality for a more significant planning time. So the approach that we use to do this, there's two parts, an offline part and an online part. So offline, we're generating these policies of varying risk. Then we're using the policies and running those and exploiting them in the domain to get an estimation of the reward distributions that you get from these different policies. And we're using information from the reward distribution to decide this criteria of when to switch to be exceeding this reward threshold, which is our goal. So this is a very brief background on risk to try to give you an idea of how these different policies are getting generated. But in utility theory, it's been studied a lot, and so if you can think of risk as almost like this plan of wealth, in the case of linear utility, this is that case of doing the expected value, and it's also that risk-neutral strategy. So if you have some wealth of 50, then maybe your utility is this one-to-one mapping where it's equivalent to what you would expect that wealth to be. So exponential functions are what's often used to model more risk. And so by choosing this delta value, you can create functions of varying convexity to represent different risk attitudes. So in the far left, you have a convex function, which is showing a risk-seeking attitude. So what you're doing is for that same utility value, you're willing to take this higher payoff, but you do so at this higher uncertainty. And then for a more conservative, risk-averse attitude, you want to have this lower payoff for that same utility, but you want to have more certainty in that because you're being more conservative. And then there's the risk-neutral case. So if you can think of utility as kind of this function that an agent is following as it's going along in the world, you can say that it's having a constant utility in the case where you're deciding to go the speed limit every time. So you're always following this linear utility. But if you're deciding to speed every time, then you're always following that convex risk-sensitive utility. So it seems more natural kind of to be able to switch between those two. And so work by Koenig and Liu studied this idea of this one-switch utility, where maybe in the case of the pizza delivery domain, you're going the speed limit, you hit some traffic, and now you want to switch between doing this risk-neutral behavior to this risk-seeking behavior. But it's kind of unclear how to know when to speed a different amount of times, and maybe one switch might not be sufficient. So we like this idea of this multi-switch utility, which is what we're trying to emulate by being able to choose between these different varying risk policies at runtime. So a little more in depth about each part of this approach. So for generating these different policies of varying risk, we're actually going to transform the probabilities by multiplying it by this exponential function. And this is actually work that Koenig did back in his thesis. So the state space is staying completely the same. And if we look at that risk-seeking case, so as you can see, if the delta value is 1, then you're not changing the transition probabilities at all. So this is that risk-neutral case. And as the delta value increases, you're getting these more convex curves. So this convexity here is increasing. So since the probabilities are being scaled by this value, the larger delta value you have, the less weight you're actually giving to the probabilities. And additionally, by the way that this curve works, as the reward is higher, you're actually giving more weight to actions that have a higher immediate reward. So if we take our probabilities from the simple pizza domain and then we convert those, we're actually shifting those probabilities to have less weight than they did before. And then in doing so, based on the cost of the risky action, in this case being cheaper for this domain, it's giving a little bit more weight to the risky. And since now these probabilities no longer add up to 1, there's an additional death state that these agents can fall into. So the basic idea here is that as the delta value is increasing, you're going to have more probability of kind of falling into this death state. So as you increase your delta value, when you're solving these policies, it's going to encourage it to choose more risky actions. And so that's how you're getting more risky actions in your policies and more risky policies. So now that we've transformed our MDP to account for these different values of risk, then we're going to take that policy and run it in this original MDP to estimate what those reward distributions are going to be. And so a little bit more information about this is that we're reasoning about the complete distribution of reward. So just the mean and variance alone in non-parametric distributions is kind of not enough to really distinguish between them. So in doing this, what we do is we take each policy, we're running it in that MDP, and for each policy we're following this trajectory. So you have a state, the policy gives you what that next action is, and then you have this next state. And then you also know your reward function, so you're getting back this discounted cumulative reward, and we're adding that. So you run a trajectory, and then you get your cumulative discounted reward at the end, and you save that off. So we're saving off these values for multiple trajectories of each different start state. And in some cases, the trajectory is going to visit the same states multiple times. And so since we are collecting these reward distributions not only on a per policy basis, but on a per state basis, we actually get a lot of savings in time by getting a lot of examples of other states during other runs. So for each policy, for each state, we have now a distribution of reward. So the red line here is the mean, and the green line is the standard deviation. This is just an example of one state for the risk neutral policy. And to sort of emphasize how these distributions can look different, so if this is our pizza domain, for different states you're going to have very different looking reward distributions. So in the beginning, you're going to have reward distributions that are a lot less because you're a lot further from the goal, and as you get closer to the goal, the reward distribution will shift to the right because you have this more chance of being successful. So now that we have these distributions for different states, they also exist for different policies. So these are showing two distributions, both for the same state, but the top one is for the risk neutral case where delta was 1, and the bottom one is for a delta value of 1.2. So it's a more risky policy. So you can see here that the standard deviation is actually, the green lines are actually more spread, which is what you would expect when you have policies with more risk because there's more variance. And the mean is actually shifted left, which is also a behavior of more risky policies, because when you lose, sometimes you lose kind of bad. Right? So taking these reward distributions, we can actually convert them into a cumulative distribution function. So this function is showing the delta value for 1, which is risk neutral, and the delta value for 1.2, which is the risky case, and it's having those both on the same graph. And to remind everyone what the CDF is showing, it's showing the probability of the distribution being less than a particular value. So at negative 80, that's a little less than 70%, and you see in the distribution on the left that it looks about 70% is actually less than that value. And you're doing the same for the risk neutral case. The probability is around 80% less, and that looks about 80% of the distribution. So that's what the CDF is telling you. Since we're interested in being above and exceeding this reward threshold, we're going to really want to pay attention to that inside line of the curve rather than the top line. And using the information from the CDF, we're going to be deciding when to switch. And so to go into more detail of that, since the CDF is giving you the probability of the distribution being less than a value, we care about the probability of being greater than the value. So you literally just take 1 minus that value. So the inside curve is the important one. So as we're going along in the environment, if this happens to be our running cumulative discount reward that we're subtracting from our current threshold, then we're going to be choosing risk neutral. In this case, we might choose either, and then in this case we'll be choosing the more risky action from that policy. So you'll see also that the more risky policy has this higher upside the risk neutral kind of never gets to, but also has this higher downside as well. So to illustrate in more depth this switching criteria, so at each time set we now have these policies, and for each state we have these distributions, and so now we're executing the policy in the world, in the environment, And as we go along, we can take a state and an action, and then we're going to ask, how do we get the next action? Well, we're going to compare the cumulative distribution function for the different policies in that state. And based on our running cumulative discounted reward, which is kind of how far we are from that threshold, we're subtracting it, we look it up in our table, and it'll tell us, okay, now take the action from this policy. And then you have another state where the distribution might look very different. So you move along, your cumulative discounted reward grows slightly, but now you're subtracting through threshold again. And so a little bit higher value is now actually telling you to take this more risk-neutral action. So results for this pizza domain, we are running 10,000 runs in this original modeled Markov decision process. So these have actually the same start state every time. And we're comparing the strategy where you're just doing sort of the expectation of the value function, which is the risk-neutral strategy, versus a strategy where you're able to switch between a risk-neutral and, in this case, a risky policy of 1.2. And we saw for a threshold of -100, and you can think of this again as related to the time you need to get to your delivery location. Here, the idea of failing is that you did not exceed it, that you actually made it under the threshold. So comparing the amount of times risk neutral is failing versus the amount of times that switching was unsuccessful, we see that the switching strategy is actually failing 9.5% less, which is reducing our losses by 30.6%. And that if we have a higher threshold, meaning we want to get there even quicker, we actually see that there's a gain. It's failing 22.4% less and reducing the losses by around 28%. So the reason behind this is we believe that higher thresholds, it's in your best interest maybe to take more risk, and so you get more benefit out of switching between these different strategies. So since the pizza delivery domain is a very simple domain, we were able to add cumulative reward to the state space. I removed the discounting to keep things discrete and whole integers, and then set thresholds for the min and max of the cumulative reward that you get. But the state space does grow quite large, and there's obviously a caveat of how you write your solver and is it threaded. But the main idea is that the planning time is significantly longer than even when we're doing these estimations of reward functions. Execution time is comparable because you're just doing this check, the CDF, which is just either a quick grab out of the graph or just a very quick linear interpolation, so the execution time isn't actually that bad. But the pros of adding the time cumulative reward to the state space is that you do get better results. It is closer to optimal. But you do so at the cost of a lot larger planning time, and this less flexibility as well. You have to know your threshold before you generate the policy, where in our method you can change that threshold on the fly. So to show the results with comparing this for the risk neutral and the switching, you see that the augmented state is actually failing 16.9% less than risk neutral, which is reducing losses by about 20%, and it's actually doing better than the switching strategy by about 6.8%, so it's reducing losses by 10%. So it is closer to the more optimal strategy if you're able to add that into the state space. So to do a more, I guess it's not necessarily realistic, but in the terms where I wasn't able to hard code the values, we applied this to a Mario domain. So Mario is going through the world, collecting coins and avoiding monsters to make it to a goal. So in this domain, I actually had to sample the state space. I defined states as Mario's relationship to other objects. I actually encoded macro actions, which uses the primitive right, left, and jump, using A* for Mario to go to these certain objects. So in Mario, the difference between a risky action and a non-risky action was one where Mario is actually going to have to collect all coins in the environment versus Mario just collects one coin. So by having to collect all objects in the environment, it produces more risk because Mario has a higher chance of dying because it's in the environment longer. So I did 1,000 runs over 1,000 runs each of 100 different worlds, because each world is generated with a different random seed, to estimate the transition probabilities and use average reward over the macro actions. And the results in terms of now taking these risky policies, estimating these reward distributions, and doing the switching, you can actually estimate the reward distributions in two ways in the Mario domain. You can do it by exploiting in the actual Markov decision process, but also by running the policies in the real simulated environment. So we have a comparison of the two. So this is over 1,000 runs in the same start state. Here, Mario has a threshold that they must get over is about 100, and we see that the switching strategy is beneficial in this case. It's failing 18.1% less, reducing losses by about 20%. And in the case of the simulator, we executed 1,000 runs over 1,000 different worlds, so it wasn't necessarily just the worlds that we were training against, and we're switching based on this discount macro action. We were using a smaller threshold, and we see there actually wasn't a lot of improvement, but there was a little bit improvement. So something to note was that the reward thresholds for this MDP Mario domain were a lot more optimistic than those in the simulator. And this is because it was showing maybe there's more coins in the environment than is actually true. So this is kind of an example of a well-modeled world and a world where things weren't modeled as well, but you still get some improvement. So for future work, we can expand this to also be integrating conservative policies, implementing it in more realistic scenarios, maybe with cheap robots, and then extending it to maybe handle these situations where you have a model and the world isn't completely accurate, which is kind of what we were seeing in that Infinite Mario Simulator domain. So in conclusion, we've demonstrated an algorithm that's able to reason and switch to exceed these thresholds, and it's doing so by reasoning about the complete distribution of reward and saving on planning time. It's showing its improved performance over risk neutral, and it's good for these domains where you're willing to take a risk, but you have this cost of maybe losing. So the main takeaway is that the algorithm actually doesn't care what kind of policies you have. It's general enough that just given some set of policies and given some criteria that might be different, but based on this idea of rewards, it can switch and decide this next best policy. So it is doing this big trade-off of the computation and less optimality for this planning by making the choice at execution time. And I will take any questions.